solve some things. So 8/6 lets our logarithms actually solve something. Ooh, I get to do this right off the bat. Gentlemen. So, when we jump into these, solve by equating exponents. Like equating exponents, what the heck does that mean? Here's how this works. My first and number one goal here is I need my bases to be the same. In other words, the value that I'm taking to the exponent's got to be identical on both sides of my equation. You're like, but it's not. That's 4, that's 8. I understand this. But is there a way I can swap that 4 around into a different form where I can have bases that are the same? So watch carefully. On this first one, 4 isn't really 4. 4 is 2 squared. And you'll probably quickly see where I'm going to end up heading with this. Can I turn 8 into something that has a base of 2? Yes. 2 to the third. That's my first step every time. Every one of these that we get into, there's a way to change the base so that they end up being the same. So here's the part that gets kind of interesting. Those bases, once they're identical, basically kind of just disappear. So I'm going to sort of ignore at this point, once I get these set, what's going on here. And I'm going to multiply my exponent times the power. I'm still doing it like an exponent rule. Okay? It's not power to power. It's not like it's 2 to the 3x. Okay, I'm just timesing them. And now I'm just going to solve this equation like I'm back in Algebra 1. 2 times 3 gives me 6x. Do a little distribute over here. And start working this out to figure out what my x value is going to be. So if I minus my 3x over and divide by 3, I get x equals 1. And the cool thing about this is I can even double check if I want to. For instance, here, if I plug in 1 for x, that's 4 to the third. 4 to the third power is 64. If I plug in 1, 8 squared is also 64. I know I'm good. So just something, again, kind of strange, but another one of the reasons I wanted us to be able to kind of play with these before and not just kind of live with change of base form. Now, will I always have to change both? Not necessarily. Like here, I'm like 2 and 32. Well, 2 I'm not going to be able to do a whole lot more to. I'm still going to put it in the parentheses just because. Nicely done. On the other side, I'm sitting here going, well, it's got to be 2 to something. Now, if you have to play with that for a little while, that's okay. But it ends up being 2 to the 5th is going to be 32. Now, again, here, the bases themselves, okay, the 2's that are here, I'm basically going to ignore now. I just have the 4x over here. If you wanted to make this 2 to the first, I guess you could say 1 times 4x. And then over here, I've got 5 to the x minus 1. Now again, you start getting comfortable and you want to skip this step and distribute right away, that's fine. But I just want to make sure we've got that foundation when we start these. And again, it's the little stuff that might get some of you on this. Like here, making sure you're having not having sign issues. If I subtract the 5x over, I've got a negative x. Or even if I subtracted the 4 over here, I'm still going to have one more step. And if I divide by the negative 1, I get 5. And yeah, sometimes these numbers can get ridiculous. Like this would be 2 to the 20th equals 32 to the 4th. They equal. I checked. But it's not one you might not necessarily be able to do in your head. Okay. So sometimes we change both bases. Sometimes we only have to change one. So let's see here. What about number 3? 8 and 16.
2.
Okay, yeah, 2. You might be tempted to think 4, but that's not going to help me with 8. So 2 to the third. And then what am I going to do for 16?
2.
2 to the fourth. You're like, ooh, I'm really going to have to get used to like these cubes and fourth roots and all that. Yeah, it's something, but the more you play with them, the more you'll get used to seeing them, and it won't be so bad. Again, sort of forget about those bases once we get them the same. Kind of like finding a common denominator if you wanted to find something similar to think about. So here, 3 times 5x would be 15x. And I'm going to go ahead and distribute here. So I'd have 12x, and 4 times 4 is 16. They're like, ooh, this isn't going to come out as a whole number. You're right. Subtract. Yeah, it's absolutely okay to leave it as a fraction. I absolutely would prefer that you would do it that way. So don't think just because you get a fraction that it's wrong. And I checked this one. That was kind of interesting too, to check what was it, 8 to the 83rds equals 16 to the, let's see, 16, 20th. Yeah, that was kind of crazy. They equaled though. They equaled. All right, last one up here. See, I like these. They're kind of fun. Ooh, what's my base going to be this time? 6. Because, okay, my 6 can stay the same. But if I play around with 216, I find out 216 is 6 to the 3rd. So again, those kind of go away. This time, no distributing or anything fancy to do. It's just the exponents. And this answer makes a lot of sense because 10 minus 7 is 3. 6 to the 3rd, we just said, is 216. So that one works. So again, a little bit of manipulation involved here, but we've got to have those bases the same somehow. Somehow. Now, this next part is where we use logs to take care of things. And again, remember, when you're talking inverses or opposites on these, ln and e, okay, are opposites, can wipe each other out. And some sort of log and its base can wipe each other out. And that may be in an exponent form, it may just be multiplying, it can vary, and we'll get to see that here. But one other thing to keep in mind. You must isolate e, or whatever I'm taking to the exponent here, first before I do an inverse. And I'll explain that here a little more in depth as we get going. But I just want to make a note of that there so I remind myself, oh yeah, before I'm taking the natural log of both sides or taking this log base, I've got to make sure that term's isolated, that's by itself on a side. And that'll actually happen in number 6. So when we get to 5, I see this 2 to the x. Well, I want to know what x is. I want to get the 2 out of there. That's my base. So to get rid of it, okay, right, now, here's what you've got to keep in mind. If I'm using log base 2 in this case, I'm not turning both sides into an exponent. Because on the left side, my log and its base cancel. Okay, there's my x. Here's where you get to use your change of base form. Because we don't know what, 7th log of base 2 is. So now is when it is okay to go ahead and divide that out that way. And again, just always watch for directions. We're rounding the nearest thousandth, so we're going to 3 decimal places. And make sure you're closing your parentheses when you're doing these. 2.807. Because if I forget to close my parentheses, I guarantee you will get a different answer, and you will not be happy about it, nor will I. So that's kind of our idea in here. Now, this next one's a little more interesting, because you might see this 10, and you're like, well, I'll just do log base 10. Not yet. Isolate first. So my first job here is to get that plus 4 out of the way. Now I can go after the 10. Okay? So anything that's furthest away from my variable term, we want to get rid of it as we go. So the plus 4 gone. Now I can deal with this sort of like I dealt with 5. I'm going to take a log of the base that I have here. So this would be log base 10, which is basically what your calculator thinks it is every time anyway. And again, I know it can be time consuming to write out steps this way, but it's also the way that it's going to click for you. Because then I see, okay, those cancel. And here will be the one other thing that's going to drive some of you bonkers. Once I get to here, don't use change of base quite yet. You're like, why not? Because now, if I do change a base right now and I round, and then I work to get into my answer and I round again, my rounding is going to put me too far off. So for right now, leave this alone. So if I'm trying to solve for x, what do I need to do next?
Add.
Okay, I need to add the 3. And we're going to get a little tight on room here, aren't we? And then my last step would be what? Divide by 2. So here's how we're going to do this. You're like, holy cow, Hardy. How in the heck am I going to get this to go the way I want to? Okay, let me get the calculator up here so you can see how this is going to work. When I go to do this, I'm going to do my change of base right here first. So even though I know, that that's naturally a base 10, I'm going to treat it like I'm going to treat every one. So if I did log 17 divided by log 10, at this point I'm going to stop. I'm not going to try to put this all in at once. I'm going to go ahead and hit enter. Okay. Now, that's just this first part. So now I want to add 3 to it. Notice we're just doing one piece at a time. And finally, I divide by 2. That's the answer I'm going to round. 2.115. Because if I would have started way back up here and changed base and rounded, and then got down here, added 3 to that, divided by 2 and rounded, it's significant. Okay? It's not like before when we were doing growth and decay and it was like a penny or something like that. It gets to be quite sizable. So you really need to wait until the end on that to make sure that we're going to be, accurate with this. So let's see. Ooh, let's throw E in. All right. What do I need to do first on number 7? Yeah, get that 3 out of there first. And once I get that out of there, now how do I dump the E?
LN.
LN, because that's its opposite. Okay, so LN and E wipe each other out. Don't start rounding yet. We never do anything with the rounding until that very last step. So I'm just going to leave that as the natural log of 5. And then my last step is to divide by 2. And this is the point where I can say, all right, natural log of 5, make sure I close my parenthesis, divided by 2. So if I'm going to the thousandths place, what's this going to round to?
805.
Okay, 0.805. So you start to see kind of where we're heading with this. Let me see, what looks like it could be problematic that we need to make sure we hit up here. Let's do 9, and we might hit up one more down here. So let's hit up 9 next, because room won't be an issue. We can kind of skip around a little bit here. All right. Anything to get away before we get rid of E?
Nope.
No, not this time. So this time I can natural log right away. Wipe that E out of there. And again, even though the temptation's going to be there, don't do it yet. Don't round. Get that 4 moved to the other side first. And there's one more little thing here and why I wanted to touch on this one. I guarantee this will happen somewhere out there.
No.
Uh-oh. Okay. The only thing I want to take the natural log of
27.
is the 27. Make sure you close your parenthesis, because that's a significant difference. So be cautious, because the last one I want to do in this section is the juggernaut at the end, number 12. Give us plenty of room to work with here. We'll kind of get rid of a number 11 so we know we got room to work with. Because we may need a little bit of space to work with. All right, so kind of do one of these. All right, 12. Where the heck do I start here? No.
Subtract 10.
Yes. All right, subtract the 10 here. Because again, whatever's the furthest away from our x term needs to go first, and we just kind of start chipping away as we get closer. So now the next closest thing is this 3. How do I get rid of it?
Distributed.
Nope, no distributing. The D, I was going to say another D word, divide. All right, we're getting there. Now how do I dump the 1.5?
Log 1.5.
Log 1.5. I cannot just divide here because that x is an exponent. It's not just 1.5x. It's 1.5 to the x. So I'm going to use the log of 1.5 on each side of my expression here. To cancel or wipe out the 1.5 base on my left side. We're actually going to be able to fit this all in one spot. And all I've got to do now is take this log and do change a base. So log of 90 divided by log of 1.5. And again, make sure you close your parentheses after the 90, or that can get you in all sorts of trouble here again. 11.098. I agree. Yeah, it looks really awful and nasty, but as long as we keep remembering, the concept is keep working and isolating my x term first, then I can use my opposite to take care of it. Should make life pretty easy here. So, oops, I kind of threw that right in the middle there, didn't I? No, this is going to be simple. All right. So, word problem. Oh, geez. Because we don't skip word problems. That just, nah. All right. We're cooking. I'm not even going to pretend how to say that. I'll say it this way. Elicha. So we have this Ethiopian stew. Damn, when you take it off the stove, its temperature is boiling. It's 212 degrees. Room temperature is 70 degrees. The cooling rate of the stew is 46 thousandths. Doesn't say how long, but okay. How long will it take to cool the stew to a serving temperature of 100 degrees Fahrenheit? Use, now you start looking at this form, it's like, holy cow, look at all these T's that are working here. But there's explanations for what everything is. So don't skip something like this. Just take your time and see what they've got available to you. So, okay. T. T is the serving temperature. How hot is it going to be when we serve it?
100.
100. Okay, so 100 equals T sub O is the initial temperature. How much was it? This 212? Minus, my room temperature is 70. See how smoothly this is going? So then we get to here, we're like, okay, e to the negative RT. Okay, 0.046. We don't know how much time.
Oh, that's 10.
That's what we're trying to figure out. Plus the room temperature.
Again.
Again. Holy cow. So I got to start working at getting this all the way back to E here. So before I do that, again, I'm going to take the time to make sure that I simplify things, because that'll probably keep me from doing something silly. And again, the 142 is just subtracting the 70 from the 212. What's next? Subtract the 70. You're going to find out these aren't such terrible problems to deal with either.
No.
You could, but I think you're going to find out here in a minute if I'm looking for something that's exact and not just like between this and this. But yes, you absolutely could go into a graphing thing, and it'd kind of be a double check too. Not a bad idea. Now what? One thing before ln, because I can't get to my e quite yet. Yep. Now remember, don't physically do it yet. You're like, what? Leave that 30 over 142. Now we're getting somewhere. Now the e is isolated, finally. What am I going to do to both sides? Natural log. Okay. So I'm going to natural log both sides of this, because that's how I dump my e. You're like, oh my gosh, Hardy. So what you're actually doing here, natural log of 30, 140 seconds. See, this is more realistic. We're not going to get some whole number answer out of this. I finally have made it to the last step, which is to divide by the negative 46 thousandths. So, mercy. When I go to type this guy in, swing over to here so we can see. I've got the natural log. Keep your whole fraction in the parentheses, because I want the natural log of that. And then you can either hit enter and then divide, or you could have just divided before. It wouldn't have hurt anything. So it's going to take somewhere in the ballpark . I'm going to assume that this is going to be minutes and not seconds. I can't imagine that's going to go from boiling to 133 seconds. I'm kind of surprised there's no mention of the time here. But that's kind of what we're looking for here. It can be a process. I mean, there it took us, what, 1, 2, 3, 4 steps before we actually could get down to getting our solution. But again, don't quit on one like this. Just kind of look at the information and work it. So finally, that needs to go away. You're going to wish they were all like part 4. Part 4 is the easiest part of this. Okay. Notice my log subbase is the same on both sides. So if I want to get rid of log base 3, how do I do it? Yeah, I just use a base of 3 on each side. The 3 and its log of same base cancel, and now I'm just left with what's sitting there in the parentheses. And then I can solve it, and then I'm done. I'm a happy camper. So I'm going to get all my x's to one side, my values to the other, and I'm going to get my answer. Kind of cool. Kind of cool. It works with logarithms. It works with natural logs.
Which you gotta use?
Except we have to use e. Because then e and natural log take care of each other. And I solve what's left. So I'm just going to write this out because we can solve multi-step equations. That's not really an issue here. I just want you to see how the opposites work here to actually get to where you can solve. Be cautious though, because I tend to find ways of putting old stuff in here. Like number 3. You're like, well, it doesn't look any different than like 1 because I just used the base. 8 and the log of 8. Square root, but let me, oh, nice, okay. When I square root this, remember, that exponent tells me, it gives me a clue. Ooh, that's how many answers there are going to be. There's 2 answers to this. So it's not only positive 4, it's also negative 4, because I could square negative 4 and get 16. So don't forget about the clue that's there to help you out with those. So again, nothing too terribly awful. So you just sort of keep bopping along here. I'm going to take a look at one more here in this middle section, because basically this copies a lot of the same things that we were doing over on the other side. So like here, for instance, if I'm looking at number 6, I want to get towards x, but the stupid log is in the way. Just use the 5. Remember, it's an exponent now, though. And that's the thing that's tricky. When it's the log and I'm using the base, it's just multiplying, and I'm canceling them out. When I use the base to both sides, these are exponents. So this is 5 squared, not 5 times 2. Now the 3x plus 1 still is itself. Yep. But I've got to remember that in this case, that's going to become an exponent. And I get my 8. Same idea working here on 7 with the natural log. Can I use e right away? Not quite. What do I have to do first? Close.
Divide by 12.
Divide by 12. If there had been a plus in there, I could have subtracted it. But since there's not, I'd be multiplying by 12. Don't do anything to that 44/12 yet. But now that I've gotten that 12 out of the way, I've gotten my coefficient out of there, now I can attack the natural log. But just like before, this is becoming an exponent. So my x is whatever value e to the 44/12 takes on. So when I go to plug that in, again, to get e, it's second natural log. And then make sure we get our fraction in there and we close our parentheses. Once that's done, we can get our solution. Okay? Never round until the final step is going to be your key on these. One last thing to throw your way.
Oh my lord.
Because sometimes you can work these out and your answers won't work. Oh, crap.
Are you?
It happens. It's math. This is how this works.
That's,
Sometimes it may. Okay, we're not dealing with the LNs. That's going to get to be a little bit much right now. So we're going to stick with logs for right now. Here's where we get to put things together, and we get to do one of your favorite things from the last section.
Brad.
Condense. So here, for instance, both logs with the same base, and I'm adding. What does adding become? Multiply. So this is actually the log of 5x times x minus 1. And again, I would literally write it out that way at the start, just kind of get used to it. And I'm actually going to simplify that before I go on here. So I'm going to distribute. Okay, haven't done anything to the right side yet. You're like, okay. Now there's one thing I got to remember here. I don't see a subbase down here. It is. If I don't see a subbase down there, we assume it's 10. So if I want to get that log of subbase 10 out of there, what do I have to do to both sides? Yep. We've got to use our base of 10, and again, we're going into exponent mode. So those wipe out. So I got 5x squared minus 5x equals 100. Uh-oh. It's coming. Everything wants to be on the x squared side. That's right. It's been a few weeks since I've gotten to say it, but here it comes. It's the Algebra 2 F word. We're going to factor this.
Yes.
So, to make my life a little bit easier,
They're all divisible.
yes, let's take the 5 out of there so this is a little easier to work with.
I love it.
And fortunately for me, all I've got to factor is what's now left in the parentheses. And this is one I could probably just do mental math on because it's a basic diamond. So what multiplies to negative 20?
4 and 5.
5 and 4. What about my signs?
5 is negative.
5 is negative. Because negative 5 plus 4 would be negative 1. So you're like, okay, I did all this work. I get to the answer, which basically is taking each set of parentheses, each quantity, and setting them equal to 0.
You gotta check it.
And we actually have to check this. Now, there's 2 ways to do this.
Plug it in.
Plug it in is an option. Or what you could do,
Good guess.
what?
Guess.
Yes. Okay. 2 ways. You can either plug them in, guess. Guess.
Negative 4.
Here's your other option. You're like, wait a minute, why is he pulling a calculator up for this? Oh, we're even going to graph this. This is going to be more fun. Here's how you would do this if you wanted to check. The left side of your equation would be the first thing you plug in for graphing. So I'd have the log of 5x plus the log of x minus 1. Oops, no. Come back. Minus 1. There we go. Then my second line is y equals 2. And what you would do then is you would take that, you'd graph it, and we'd look to see where the intersection point is. So, if you want to check this way instead of plugging in, here's how you do it. Once you got here, you'd hit second trace. You remember we used to find zeros and all that other stuff before? Now we're just looking for the intersection point. So we're going to go to where it says intersect. Once we get there, we're going to hit enter. Now this isn't as complicated as it was before. Because now, there's my little curvy guy. He's kind of on my curve here. Why do I keep doing that? You can't see me when I point there. Here. This curve here, okay? I just hit enter to let it know that's the first curve I'm checking. And then if I hit the up arrow, notice it goes to the straight line.
Yeah.
Just anywhere in there, hit enter twice. And if it doesn't freeze like it just did, technology is wonderful.
5 more. I mean 5. 2.
How can an online calculator freeze? Well, it just did. Quit freezing.
Forward.
Are you serious right now? It's going to make me start over. This is a lesson to those of you listening later. Technology is wonderful, but sometimes just manually doing things is so much easier. All right, let's try this again. First curve. Am I on the line now? No. Now I am.
Wait.
Hey, all right. So the intersections where x equals 5. Notice where x equals -4, this isn't going to cross anywhere. Ugh. This isn't going to cross over here at x equals -4 anywhere. So visually I can see that one doesn't work. Otherwise, if I plug those in, I could algebraically figure out the same thing. So, your task, whether you choose to take it or not.
What's your shit?
I've got it written on the back board, I've got it written on the front board, but I'm going to write it here too, so in case you're not remembering and you look later, I'll have it on the website anyway, but I'll write it here just in case you don't care to look in either of those places. We're on page 505. And again, I guess when you look at it that I'm hand selecting problems, that makes it a little more of a pain to write all this, but again, we'll survive. So those are the problems that we are on the lookout for. Now again, even though you've got a work day tomorrow, just a few. Maybe it's not all 11 of these, but like 2 or 3 of them. Just to kind of play with them a little bit, and then tomorrow will be a lot easier.